Hi everyone. In this video, we'll develop strategies for applying L'Hopital's rule to the indeterminate forms of exponential type. So far, we've developed the following strategies for each of these different types of indeterminate forms. For the fractional types, 0 over 0 and infinity over infinity, we can just directly apply L'Hopital's rule. For the other types, L'Hopital's rule can be used as long as we're able to convert to one of these fractional types first. For infinity minus infinity, that's typically done by using log rules or by forming a common denominator. For 0 times infinity, it's done by changing the product into a quotient using a negative exponent. And we have yet to talk about these last three, which I'll collectively refer to as the indeterminate forms of exponential type. When you encounter one of these, I suggest the following strategy. Apply a logarithm. After doing that, we'll be in a better position to convert our limit into a fraction to use L'Hopital's rule, as we'll see in some examples in just a moment. But of course, we can't just apply a logarithm without expecting to change the value of the limit. So we would then need to also apply an exponential to cancel out the act of taking a logarithm. After all, applying an exponential represents the inverse of applying a logarithm. So if we do both, then we didn't really change anything. Let's try out this strategy by calculating the limit as x approaches infinity of x to the power of 1 over x. As always, we start by just letting x approach infinity and seeing what happens. In the exponent, we see 1 is getting divided by a quantity which is getting larger and larger, which would result in the exponent getting closer to 0. Infinity to the 0 is one of our indeterminate forms of exponential type, so we'll try out the strategy that I just proposed. That strategy was to apply a logarithm. So start with a limit of x to the 1 over x that we've been asked to calculate, and then apply the natural logarithm. It really can be a log with any base, but the natural logarithm is just the easiest to work with. Now, this does change the value of the limit, but we'll make sure to cancel out this logarithm later on. For now, let's just find the value of this limit as it's currently stated. The advantage of this logarithm is that it allows us to pull the exponent in front. After doing that, we see that we're now taking the limit of a product. And that's good because a product can always be turned into a quotient, which might allow us to use L'Hopital's rule. But first we need to check that we have permission. So you can pause and double check that this limit does provide a result of infinity over infinity, which means L'Hopital's rule is applicable. So in our numerator, we take the derivative of ln x to get 1 over x, and in the denominator, we get 1 as the derivative of x. And this boils down just to the limit of 1 over x, which is pretty simple. So now when we try to evaluate the limit again, we find 1 is getting divided by an increasingly larger value, which would cause the result to get closer to 0. We've found a value for this limit, but be careful. We're not finished yet. After all, what we were asked to calculate is the limit of x to the 1 over x, but what we actually found was the limit of ln x to the 1 over x. We shouldn't expect these to represent the same value. So as I suggested before, we need to cancel out the act of taking a logarithm by applying an exponential. As long as we apply both the natural logarithm and the natural exponential, these inverse operations cancel each other out. So we could be assured that these limits are equal in value if we did that. Now we already found the limit of ln x to the 1 over x, and we found that had a value of 0. So after taking the limit, this all results in e to the 0, and e to the 0 is the same thing as 1, and this represents the value of our original limit. To make a long story short, whenever you apply the natural log at the beginning and then calculate the value of the resulting limit, as a final step, you need to take e to the power of that value to get the answer to the original question. Here's another example. Pause and try it for yourself, and when you're ready, let's continue. As always, the first step is to try evaluating the limit. In this case, we see 1 over infinity, which represents a quantity approaching 0. So this ends up taking the form 1 to the infinity, and you can go back and check that this is an indeterminate form of exponential type. That means we should start by applying a logarithm, or at least it's worth trying. So we take the ln of our function with recognition that this does change the value of the limit, but we'll correct that problem later on. After applying our logarithm, we can bring this exponent in front just like before, resulting in a product of functions. If we want to use L'Hopital's rule, we need a quotient, but we can make that happen by introducing a negative exponent to bring one of these factors down into the denominator. Be mindful that you get to choose which factor to bring down, and in this case, the best choice is to bring down the 5x. But when we're finished the example, I encourage you to try bringing down the logarithm instead so that you can gain some intuition about why 5x was the better choice. But for now, I'll just tell you that it's the better choice and we'll go with it. Now, 5x to the minus 1 can be viewed as 1 over 5x, which could make it easier to evaluate this limit. Notice 1 over 5x is going to approach 0 when x goes to infinity. And since ln of 1 is 0, this results in the indeterminate form 0 over 0. And that's good, since L'Hopital's rule is applicable to this result, so let's do it. Start with the derivative of the denominator, which you can check is negative 1 over 5x squared. And then in the numerator, we recognize the derivative of ln of something is 1 over that something. But then, according to the chain rule, we need to multiply by the derivative of 1 plus 1 over 5x, which is the inside part of the logarithm. So the derivative of 1 is 0, and we just saw that the derivative of 1 over 5x is negative 1 over 5x squared. Now that we've applied L'Hopital's rule, we check for easy simplifications and then try to evaluate the limit again. First, we can cancel out this common factor. And now let's see what happens when x goes to infinity. When we do that, we get a clean result of 1. But this is not the answer to the question. At the end, we still need to apply an exponential to cancel out our application of the logarithm. So to get the limit we actually want, we take this value we just found, which is 1, and then take e to the power of that value. E to the power of 1 is just e, so this represents our final answer. And that's it for L'Hopital's rule, so I'll wrap things up here and see you next time.